Hi, for a while I've been wanting to do an extreme teardown on the Flir Lepton sensor used in the Flir 1. Haven't really wanted to rip apart a good sensor, but thanks to Sashi at Pure Engineering, who do the breakout boards for these, he sent me one to pull apart, so let's take a look at it. In the original teardown I only went as far as pulling the lens off, and you can just about see the sensor but not much else, so time to crack the cover off. Cracked off. So on this side we can see the thermal sensor, which looks like it's been dye bonded to the ceramic substrate. Just a few capacitors in there. On the back side there's this one control chip, which I'm guessing is probably a custom chip. Interesting little group of 9 test pads there, so might be interesting to try getting a setup that will probe those at some point. So I'm not going to do it now, but it might be interesting to see what's floating around on those pins. Now, looking at the cover, from the outside we can see these connections which are for an external shutter for field correction, which we've seen used in the TG165. And also inside we've got some shielding, but the other thing, there's also a little thermistor in there, so that's obviously sensing the temperature close to the lens to provide a reference temperature. It looks like these are probably put down with conductive ink, although this thermistor looks like it's soldered. It's a bit hard to tell. That's looks like about an 0402 thermistor. A bit hard to tell how they've done this, and this is a very thin metal coating, so I wonder if this is actually a some sort of process where the metal is somehow deposited directly onto the plastic. I can't see how they could have done this if it was a foil or something. It seems to be pretty thin. I can't sort of actually get any of it off, so it's some sort of clever sort of selective metallization process they've used. It looks like the sensor's sort of a couple of layers. We've got the top, which will be the window with the sort of vacuum cavity, and then the actual die underneath it, which is the sensor, plus, comparing with the other Flir sensors, maybe the A to D converter on there. Right, if we take a close look at the die around the cover, it looks very, very similar to what we saw on the E4 sensor. Got a date ISC 1101N, copyright 2012, date on there. Some various sort of layer type markings, and I presume test pads there. And we see some of the pads that have got bond wires. Actually, we've got a bond wire, and it looks like we've got a test pad next to it in each case, with complete with a number on there. And you see various structures on. I think it's a pretty sure bet that, like on the E4, all the analog stuff, the A to D converter, is integrated onto this die, and that chip at the backside will just be processing the digital data stream, and maybe doing some analog power supply or something. But I'd imagine they've probably integrated this pretty well, so this die handles all the analog stuff and just squirts out a digital data stream for the other chip to pick up. This bit, I'd imagine this is probably just something showing all the various sort of process stages, so something sort of appears in the box on each layer of the processing. Just got the Flir logo there. Again, IC 1011 2012. Can't really tell much about what all these structures are, but they do look quite familiar compared to the E4 sensor. Right, if we take a close look at this side under the microscope, we can actually see that the sort of top piece, the main die is on the right and we've got a spacer. So the question is the cavity, the sort of vacuum cavity above the sensor, is that spacer just a ring, or is this piece on the left actually machined out, or is it just a solid slab? So see if we can get some more info by doing a sort of sideways x-ray of it. Well, this is about the best image I can get, and I think you can just about see sort of the spacer in there. There's no obvious change in density within that top slab, so it looks like that middle piece is what's creating the vacuum cavity above the sensor, and the top is just a flat slab. Well, it looks like there's a little bit of an overhang on that top thing, so I'm just going to see if I can just crack it off. I'm not having much luck on cutting it. Obviously silicon and whatever they bond it with is very hard. I just remember I had this thing, I bought this long time ago. I'm not completely sure what its original application was, but I believe it's for cutting tiles. It's basically an ultrasonic head. So, and I think the idea was that you use it for scoring. For example, this is a piece of glass. You can use it for scoring, for sort of score and snap type cutting of glass and tiles. I'm not quite sure what benefit this has over a traditional diamond wheel, but I'm just wondering if I can maybe use this as a sort of almost like a sort of miniature jackhammer type thing to sort of break away the silicon sort of in small pieces without destroying everything else. So I'll give this a go and see how we get on. Seems to be sort of working. I'm going to have to do the rest of this under the mantis. I can't really work through the camera, unfortunately. Could do with a really good trinocular magnifier, so if Vision Engineering or Tagan or anyone's listening, I'm more than happy to accept donations. Right, so it looks like we've been moderately successful in chiseling that window off. Just take a sort of quick overview. This is the main array. I've sort of deliberately blasted some of the sensors off just so we could see both above and below the sensor, slightly less drastically than I did with the Seek die. There's sort of quite a lot of detail on there. So there's just a general overview. I'll flip to a high magnification in a minute. So you can see there's some of the remnants of the that spacer. I'll try chiseling a bit more off, but I want to get enough shots, get plenty of shots first in case I end up destroying it completely. So we'll look at a high magnification. So we've got a few interesting looking features around here. I've no idea what these are, maybe they're reference pixels or something, but there seems to be quite a few blocks of similar things. But then as we actually get to the actual array, it's actually quite nicely they actually label the row and column numbers for us. So there's a big block there, and then we've got the main array here. Again, there's another sort of area there. One of these blocks sort of surrounding it are perhaps some reference type things. Again, that's the area where I've blown away. So the dark green are the actual sensing pixels on their sort of supports to provide thermal isolation. And then we've got a great big area. I don't know if that's maybe some sort of shift out type arrangement, or perhaps a row or column driver or something. It's sort of quite a large feature there on the long axis of the array. Let's see if we can get a closer look in at the actual pixels. And say here we can actually see the close-up of the pixels. Say the dark ones are the pixels that are there, and the light area are the ones that have got blown off when I gave it a blast of compressed air. So if we can magnify this, you might just be able to see the sort of supporting arm structure for each pixel that it sort of floats on to keep it thermally isolated from the neighbouring ones and from the die. Right, this is about the best picture I managed to get of the actual pixels. You can see the supporting structure, which is the light coloured traces, and then the sort of presumably wires down to layers below for the interconnect. On this drawing I've just coloured in some of the paths, so it looks like the pixels are actually wired in a sort of series chain, sort of horizontally. So presumably these are basically going to be resistive elements. so I'm not sure how they actually read that out, but obviously they need to optimise the number of interconnects to avoid taking up too much space on the die. Right, see if we can find out anything about this chip on the other side. I'll just blast it with some hot air and see if we can. Looks like it's got some underfill adhesive, so hopefully we can soften that and melt the solder to get it off. Well, it's proving to be a real pain getting this underfill off this chip. I've sort of left it overnight in dichloromethane, that seems to have softened it a little bit. So I'm literally just having to scrape the remains off a small piece at a time, which is getting somewhat tedious. Right, I've got a lot of this underfill off, still not quite there. You can see there's a few different layers, so I'm not really sure exactly what the typical structure is of these sort of chip scale package, but it looks like there's a sort of top layer with the solder balls that's then sort of fairly large sort of features, and here we can see it's broken through to the die underneath. So I've just been sort of scraping away, so we've got sort of scrape marks on the solder balls. So you can see some of the die. So for example there we've got that top layer in the sort of brown, and then the actual die underneath. Just wanted to get a few shots of this before going any further, just in case I end up destroying it. Can't see any obvious markings that might identify it yet, but again that's probably going to be on the layer underneath. Right, after a bit more scraping I think we can see a bit more clearly how this sort of CSP package is structured. Pretty much all the top metal is now sort of flattened off, so you can see we've got some sort of fairly big traces that then go to the edge to sort of bond down to the lower layers, which is obviously much higher density. So you've got some fairly thick ones. These are probably going to be the power and grounds. These sort of thick traces here. Still haven't found any obvious identifying marks or text on it. You can see some of the structure underneath. Hard to really tell that much about it, other than it's probably not just an FPGA, because it just looks, an FPGA you'd expect to be very uniform over a lot of the chips. Most of the die would be the actual logic cells, although yeah, we do have some quite uniform sections up here. Again, we're looking at the sort of pinkish stuff, not the silver top layer. But it's a little bit hard to tell. So you can clearly see sort of the way this, over this side we've got these traces going from the balls. So we've managed to scrape off the joins to the rest of it here. For example, here you can see these sort of three balls here go to the sort of wires over at the edge down to the main die. And obviously this I imagine this sort of ball thing is the last stage of the process, so they can probably use the same underlying die and either bond it out into a more, you know, say a QFP or whatever package, or put this extra layer on top to do the CSP package type. Right, I've sanded this down a little bit with some 3 micron lapping film. You see a few more features. I've had a very sort of thorough going over it. I can't find any text at all in the bits that we could see. There are a few sort of features. I don't really know enough about this sort of stuff to identify them, but there seems to be, there's a lot of these blocks here now. Yeah, it's plausible these may be sort of macro cells or something, but they seem to occupy quite a large section of the chip. Although it could just be that these are just a layer, because there are quite a lot of layers. There's a few places where, you know, I've scraped through quite a few layers, and there does seem to be quite a difference in complexity at each layer. So we've still got a few bits of that top sort of ball grid layer on there, but if we go over, so we can see quite a lot of the detail below it. You see there's much finer detail on some of the layers below that, but I think probably the best bet, in, you know, if this is a standard chip rather than a custom, then probably just the fact that it's in a 56 ball chip scale package, you know, may well identify it. I've had a look, I can't immediately find any FPGAs that match it. There is a Xilinx CPLD, but I don't think it's got anything like the complexity it would need to have to do this. So my guess would be, looking at the data rates, you know, probably a DSP or a sort of mid to high end microcontroller, but it may well be a completely custom chip. Although if it was, I would expect to see, you know, for them to have stuck their name on it somewhere. I'll give it one more sort of scrape down to see if I can find anything, but I think that's probably going to be it. Again, here you can see a nice little bit of extra detail on some sort of layers below. Well, I think that's pretty about it for trying to ID what this chip is exactly. So just sort of lower magnification, we can see some sort of blocks. There's sort of quite a few of these blocks here, which I'm guessing are probably memory of some sort. And it clearly has, you know, flash memory, or probably flash. It's not totally certain that the firmware is updatable on this, but I think it seems fairly likely. I've seen multiple mentions of different firmware versions, so I think it's highly likely there's flash memory on it. There's clearly some RAM, there's some processing capability for the data, so sort of the die sort of seems to have quite a lot of different areas, so I don't think it's, certainly if it is an FPGA, it's not just an FPGA, it's maybe an FPGA with some sort of, you know, a processor on there or some other stuff, or, you know, a processor with some programmable stuff, or just a DSP. So there's a few sort of distinct, sort of fairly isolated blocks, but there isn't like the huge uniform field of stuff that you'd expect to see on a pure FPGA. So my best guess is it's either a full custom chip, probably with a processor on it somewhere, or just a processor or DSP. If anyone can come up with some suggestions of chips which are in a 56 pin 7x8 ball CSP, it wouldn't be too difficult to eliminate those by the pin out, because we've still got the ceramic base that it's on, so we could easily sort of look at the continuity between the balls and the things like the clock and power pins. So if it is an off-the-shelf chip, then it shouldn't be too difficult to identify it. And so all we've got left is this ceramic hybrid module. So it's quite interesting in that it's got sort of the sort of cavity in the bottom, which is presumably why they didn't do it using a PCB. If we take a look at the X-ray, it looks like there's about 4 layers of metallization on here. I did actually try doing a side-on X-ray, but I couldn't get enough penetration to look at the layer structure. But it looks not dissimilar to a multi-layer PCB, just with ceramic. I don't really know what the manufacturing process is for these, but it's a not uncommon process. And this is the lens assembly. Just a tiny little lens, and interestingly there seems to be a filter of some sort on the back of it. Don't know if maybe that's a visible cut, or maybe for shaping the sort of spectrum of infrared that it passes. Now interestingly, that back bit wasn't just a filter, it looks like it's actually a 2-element lens. It's just got a flat on the rear, and with an anti-reflection coating. Coatings are quite important in infrared optics, because without it you get quite substantial losses. So pretty much all infrared lenses do have some coatings on them to prevent them reflecting a lot of the infrared they're trying to pass. And there's this one. Actually, I think this might have been the one in front, because this has got a, so we've got the coating on that side, but also we've got like a concave part on the back, so that's quite interesting. That's actually a 2-layer. I'm not sure what this material is. It could be sort of germanium, chalcogenide glass, maybe silicon, and the fact it's in this sort of flat, sort of square format would suggest that it maybe is a silicon or germanium. So I think chalcogenide glass tends to be sort of moulded, and if you're making a moulded lens, I don't see why you would make it square. Whereas if it was a sort of silicon and germanium sort of made on a sort of wafer type process, then obviously it would be done as a large array of wafers and then just diced up. And looking at the side, it does sort of look a bit like it may be silicon. It is actually slightly conductive as well. It measures a few tens of K side by side. So yeah, so I wonder if that's silicon or germanium. Unfortunately, I no longer have that X-ray fluorescent spectrometer, so I can't measure it easily. Well, that was moderately interesting. I think we've probably voided our warranty here. There is, I have it on good authority, there is a new version of the Lepton coming out fairly soon in the new Flir 1, which will be 160 by 120, which should be quite interesting to take a look at. I'd imagine the sort of the construction is going to be very similar, but so we've seen from the die that that is genuinely an 80 by 60 array. It's not a crippled high-res array or anything. It's genuinely an 80 by 60 sensor. But also it'd be interesting to see if the 160 by 120 has a larger array, or whether they've gone to a high density. Because one issue with infrared is it's difficult to make an infrared, because you're detecting wavelengths in the sort of tens of microns sort of region. It's difficult to make a sensor with dimensions smaller than that, just because it needs to be bigger than a wavelength. And I think the Seek sensor was pretty much pushing at those limits.